Okay, looks like we're live. Excellent, excellent, excellent. So, we are going to finish up these Chapter 6 problems. There were quite a lot of them. First up, problem 84. Urea. Urea. Substance commonly used as a fertilizer, it's P, has the formula CH4N2O. What is its percent composition by mass? All right. So, percent composition. First, we need its total mass. So CH4N2O. Okay. It's percent composition by mass. So 1 times 12.011, 4 times 1.0079, 2 times 14.007. Okay, yes, you can hear me. Good. 1 times 15.999. You can hear me, but you can't see what I'm writing. All right. Gives it a total mass. Bring up handy dandy calculator. There we go. Why are you not coming up? There we go. So, and why is this so invisible? All right. There we go. That'll do it. All right. Okay. Plus 4 times 1.0079 plus 2 times 14.007 plus 15.999. Total mass of, really, 12 plus 28. It's going to be 40 plus 16 makes 56 plus 4. Yeah, okay. 60.056 grams per mole. So, of that, carbon is 12.011 over the 60.056. Hydrogen is 4 times 1.0079 divided by 60.056. Nitrogen is 28.014 over 60.056. And oxygen is 15.999 divided by 60.056. So 19.999. Yeah, that rounds up, so it's going to be 20.000% carbon. 6.7131% hydrogen. 46.646% nitrogen. And 26.640% oxygen. That should add up to 100. So 20, 46, 72, 73.3-ish. I forget. What did I screw up? How did I screw up? Did I screw up? No, I didn't. Okay, it adds up to 100. I'm just not doing good at adding up numbers in my head today. All right, so that's how you find the percent composition of a substance. Not particularly difficult. You just need the total mass, and then it's just the fraction of each element gives you that percentage. All right, what problem is next? 84 is followed by 86. An unknown substance, or an unknown liquid, is composed of 5.57% hydrogen, 28 point. Okay, so we're just going to go ahead and they give us the percent composition and they give us the molecular weight. So what is the formula? We're just going to go ahead and go directly there. So hydrogen is 5.57%. Chlorine, they say? Yes. Chlorine is 28.01%. And carbon is 66.42%. And the molecular weight is 126.58. Okay. .57% of 126.58. Shoot. 28.01% of 126.58. And 66.42% of 126.58. All right. So now we divide by the atomic mass of each of these. So 1.008, 35.45, and 12.01 gives us 7, 1, and 7. Really? That's a... Okay. So that means it's C7H7Cl. So that is just a direct method, if they give you the percent composition and the molecular weight, to get from percent comp, molecular weight, you can go pretty much directly to the molecular formula, which in this case is the same as the empirical formula. All right, 88. What is the empirical formula of stannous fluoride? The first fluoride compound added to toothpaste to protect teeth against decay. Its mass percent is blah, blah, blah. Okay. 24.25% fluorine, 75.75% tin. So, okay, in this case, they didn't give us the molecular weight, so we're just going to have to find the empirical weight. So we change from percentages to grams, and we divide by the atomic masses. Bum, bum, ba-dum, bum, ba-dum, bum, ba-da-dum, bum, ba-da-dum. 18.998, and first 10, 118.71. Oops. 25, nope, 4.25 divided by 18.998. 1.276. And 75.75 divided by 118.71 is 0.6381. Now we divide both of these by the smaller number. Hello, puppy dog. You are going to lie directly at my feet. That is only mildly inconvenient, and I'm actually okay with it. You're a sweet puppy dog. Yes, I love you very much. So that means that this is SnF2. Because barring rounding errors, it's a 1-to-2 ratio. So these problems aren't particularly difficult. It's just math, 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 math. Okay. So next up is 90. Combustion analysis of 45.62 milligrams of toluene, a commonly used solvent, gives 35.67 milligrams of H2O and 152.5 milligrams of CO2. What is the empirical formula of toluene? Okay, so we started with 45.62 milligrams of our toluene. We have 35.67 milligrams of H2O. So we convert that to grams. 1 gram per 1,000 milligrams. And then we convert that to moles of water. So 1 mole of H2O for every 18.02 grams of H2O. And then we have to convert from that to moles of hydrogen, because we're not cared about the water so much as the hydrogen, and there are 2 moles of hydrogen for every 1 mole of water. Don't forget that too. So 35.67 divided by 1,000 divided by 18.02 times 2. 3.959 times 10 to the negative third moles of hydrogen. And then the carbon dioxide was 152.5, yes, 152.5 milligrams of CO2. Divide by 1,000 to convert to grams. Then we convert to moles of CO2. Let's see, that's 40. No, let's just be safe. .01 grams of CO2. And then there's just 1 mole of carbon in every mole of CO2. So 152.5 divided by 1,000 divided by 44.01 gives us 3.465 times 10 to the negative third moles of carbon. Oh, bother. How did I screw up? Because toluene doesn't have any oxygen in it. Well, let's just double check on my math. Let's see, water. 18, yep. 35.67 divided by 1,000 divided by 18.02 times 2. 3.959, yep. 152.5 divided by 1,000 divided by 44.01, 3.465. Well, let's check and see if there's any oxygen in there. I mean, to be safe, I should do that no matter what, but okay. How many grams of hydrogen is this? 0.003959 times 1.0079. That is 3.99 milligrams of hydrogen. 0.003465 times 12.011 is 4.161. No. Yeah. 41.61 grams of carbon. We add those together. 0.654. Yeah, okay, so there's no oxygen in there. Let's see. Well, let's just go ahead and give this a shot. We're going to divide both of them by the number of moles of carbon. So 0.003959 divided by 0.003465 gives us a 1 to 1.143 ratio. That looks to be about 1 to 7. So multiply. This is all right. So we multiply both of these by 7. We're going to get C7H8. I think so. Times 7. Yeah. Which is not the formula of toluene. Toluene. One, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Oh, that is the formula of toluene. Okay. This is a particularly unkind problem because that's a weird ass ratio. I mean, that is the actual ratio that you would get. It's just very weird. And I don't know how easy it would be for you guys to recognize that this is a 1/7 sort of thing. I did because I'm kind of a geek. I'm just aware that the 1/7 is 142,857 repeating. So I mean that's just the way it is. I mean, this is the actual empirical formula and the actual molecular formula of toluene, so it would give you that ratio. I just find it particularly unkind to give that to you in a problem like this. All right. In any event, let's continue with the thingamabob. So let's see, that was 88. Next up is 90. Oh no, that was 90. 90 is followed by 94. Disilane, Si2HX, is analyzed and found to contain 90.28% silicon by mass. What is the value of X? So, disilane, Si2HX, is 90.28% silicon, which means it is going to be 9.72% hydrogen. Let's see. I wonder if there is a clever way to do this. Where's periodic table? 2 times 32. Oh, that's sulfur. 2 times 28.085 is equal to 90.28% of N. So N equals 2 times 28.085 divided by 0.9028. Okay, what I'm doing is basically I'm finding the molecular weight of, or the molar mass of the disilane. So 2 times 28.05, or sorry, 85, divided by 0.9028 gives us 62.22. So now let's just go ahead and subtract the mass of the silicon, which was 56.17. 6.05 grams of hydrogen. So now that's going to give us, we divide by the molar mass of hydrogen equals 6. So it's Si2H6. Probably doing the percent composition stuff, we could have done it the exact same way, but no particular need to, when they've given us half the information already. I'm confident that I'm right on this one. Nevertheless, that was 94, Si2H6, yes. Okay, so what comes next? Who is next? Who? 100. How many moles of solute are present in each of the following solutions? We're finally up to solution chemistry. Okay. 35 mils of 1.2 molar nitric acid. So 35 mils is 0.0350 liters times 1.200 moles per liter. Remember, molarity is moles per liter, which is why I converted that to liters. 1.2 times 0.035 is 0.0420 moles of nitric acid. And then B, 175 mils of 0.67 molar glucose, so that's 175 liters, times 0.67 moles per liter. Zero point 0.12 moles. They only gave us two sig figs. All right, so that is that. Remember, when it comes to concentration, molarity is moles over volume, so moles is molarity times volume, and volume is moles over molarity. After 100, we do 102. How many milliliters of a 0.45 molar barium chloride solution contains 15 grams of barium chloride? All right, so 15 grams of barium chloride, we need to convert that to moles. So we need the molar mass of our barium chloride. Moles per gram. So barium, 137.33. (208.23 grams per mole). 0.0720 moles of our barium chloride. So now we know our concentration, and we know our moles, so we can find volume. Volume equals N over M. 0.0720 moles divided by 0.45 moles per liter. .16 liters is 160 milliliters. Remember, they asked for it in milliliters rather than liters, so that's the correct answer, milliliters. So after 104 is 106, 102, 104, 106. So 104. The sterile saline solution used to rinse contact lenses can be made by dissolving 400 milligrams of sodium chloride in sterile water and diluting to 100 milliliters. What is the molarity of the solution? Okay, so that's 400 milligrams of salt in 100 milliliters of solution. So once again, we need to convert to moles. So 400 milligrams is 0.4 grams. So now we divide by 55.99. See, 22.9. Oopsie, no, definitely don't do that. 22.99 plus 35.45, 58.44. 6.84 times 10 to the negative third moles of NaCl. Now we divide by 100 milliliters, or 0.1 liters, is 6.84 times 10 to the negative 2 molar. They are not as careful about sig figs as I am. Okay. Double check my math. 104.0685. Yep, rounding. 106. Copper reacts with dilute nitric acid according to the following equation. Copper plus nitric acid makes copper nitrate, nitric oxide, and water. If a copper penny weighing 3.045 grams is dissolved in a small amount of nitric acid and the resultant solution is diluted to 50 mils with water, what is the molarity of the copper 2 nitrate? Okay, well, 3.045 grams of copper. The molar mass of copper is 65 something? 63.546. How many moles of copper is that? Zero 0.04792 moles of copper. All right. So there's our moles of copper. And we have a volume of our solution. Yeah, 50 mils. All right. Now here's the thing. They give us moles of copper, but they ask for the concentration of the copper nitrate. And if you look at this equation, 3 moles of copper turns into 3 moles of copper 2 nitrate. So we don't, I mean, technically we do need to convert, but it's times 3 over 3. Because it's 3 moles of copper 2 nitrate is produced for every 3 moles of copper consumed. So no skin off the nose there. So 0.04792 moles of copper 2 nitrate divided by 50 mils is 0.0500 liters. Gonna be about, yep, 0.9584 molar. Surprisingly concentrated. All right, what comes next? Who is next? 108. A bottle of 12 molar hydrochloric acid has only 35.7 mils left in it. What will the HCl concentration be if the solution is diluted to 250 milliliters? Well, that is just a M1V1 equals M2V2 problem. Dilution, this is just really straightforward. So we know our initial concentration, our initial volume, and our final volume. We're looking for our final concentration. So M2 equals M1V1 over V2. 12.0 molar times initial volume was 35.7 mils. Final volume was 250. Yes, 250.0 mils. And now we see why you don't have to worry about converting back to liters for this and kind of only this, because mils cancels. All right, is going to be equal to what? Let's break out the calculator. 12 times 35.7 divided by 250, 1.71 molar. Okay. And after 108, 110. A flask containing 450 milliliters of 0.5 molar hydrobromic acid was accidentally knocked to the floor. Quit licking me, dog. How many grams of potassium carbonate would you need to put on the spill to neutralize the acid according to the following equation? Okay. So 0.450 liters times 0.500 molar means we have 0.225 moles of hydrobromic acid on the floor. Now we convert that to potassium carbonate times 1 mole of potassium carbonate for every 2 moles of hydrobromic acid is equal to 0.113 moles of K2CO3. 1125, but 3 sig figs. And then we convert that to grams. I do not know the molar mass of potassium carbonate off the top of my head. Potassium 39.098. 39.098 times 2 plus 12.011 plus 15.99 times 3. 138.204 grams per mole. Bog standard Stoich problem times 0.125. We're going to need 15.5 grams of potassium carbonate. Okay, who's next? That was 110. Next up is 114. Ringer's solution, used in the treatment of burns and wounds, is prepared by dissolving 4.30 grams of sodium chloride, 0.150 grams of potassium chloride, and 0.165 grams of calcium chloride in water, and diluting it to a volume of 500 mils. What is the molarity of each of the component ions in the solution? Okay. So the ions we have are sodium, potassium, calcium, and chloride. So okay. Don't scratch yourself right next to my chair like that, buddy. It's annoying. All right. 4.30 grams of NaCl divided by 58.44 grams per mole. And then we have potassium chloride, 0.150 grams of KCl. And how much calcium chloride? 0.165. 0.165 grams calcium chloride. $39.098 plus 35.45. 75.55 grams per mole. And calcium. 40 something? 40.078. 40.078 plus 35.45 times 2. 110.98 grams per mole. So 4.3 divided by 58.44. 0.0736 moles of NaCl. 0.15 divided by 75.55. 0.0199 moles of KCl. And 0.165 divided by 110.98. 0.00149 moles of calcium chloride. Now, that means that there are 0.0736 moles of sodium, 0.00199 moles of potassium, and 0.00149 moles of calcium. But for the chloride, we need to add this and 2 times that. Because when these dissolve in water, you get 1 chloride for every unit of NaCl, 1 chloride for every unit of KCl, and 2 chloride for every unit of CaCl. So 0.00149 times 2 plus 0.00199 plus 0.0736. So we're going to get 0.0786 moles of chloride. All right, so that was 114. Next up, 116. The estimated concentration of gold in the oceans is 1 times 10 to the negative 11th gram per mil. Express the concentrations in moles per liter. All right. 1.0 times 10 to the negative 11th grams per milliliter. Well, it's going to be easy to switch to liters. So 1,000 milliliters per liter. Then to switch it to moles, we're going to need the molar mass of gold. Gold is 196.97. 196.97 grams per mole. So when we do that, milliliters cancels, grams cancel. Love it, doggy. I love you, buddy, but I'm doing something. I'm busy. I'm working right now. All right, so oops, need the calculator if I'm going to do calculations. My dog is being very, very needy for affection at the moment. Although the possibility also exists that he might need to pee. All right, so 0.12345678910. So that's 1 times 10 to the negative 11th. So now we multiply by 1,000. Oops. So now we multiply by 1,000. And then we divide by 196.97. And that is 5.0, well, technically 5.1. They only gave us 2 sig figs, times 10 to the negative 11th molar. Yes, there is gold in salt and ocean water, but such a small amount that it's really, really not worth it to try and get it out of there. All right. What comes after 116? Okay. But I'm working here, buddy. Yes, I love you. You're a good boy, Wesley. 118. Give the percent composition of each of the following substances. I'm not going to do that one. That's going to take forever. That's just a lot of arithmetic. I mean, finding percent composition is not particularly difficult. You just find the total mass and then divide the mass of each element out into that total mass. It's simple enough. You guys are smart enough, aren't they, Wesley? Aren't they, Wesley? Yeah. So what comes after 118? 120. Okay, that's a typo. It's not 1,206. It's 120. Okay. The reaction of tungsten hexachloride with bismuth gives hexatungsten dodecachloride. Dang. Balance. Stop, buddy. All right. Balance the equation. WCl6 plus Bi yields W6Cl12 plus BiCl3. So we need 6 of these. That gives us 36 chlorines. We only have 12. We need 24, so 8 of these and 8 of these. All right. How many grams of bismuth react with 150 grams of tungsten hexachloride? So 150 grams divided by the molar mass of tungsten hexachloride. Tungsten is 183.84. Whoa. 0.84 plus 35.45 times 6. 396.54 grams per mole. So 150 divided by 396.54, 0.3783 moles of tungsten hexachloride. And the bismuth, it's an 8-to-6. So now we convert 8 moles bismuth for every 6 moles of the tungsten hexachloride. Yeah, okay. So times 8 divided by 4 divided by 6. 0.5044 moles of bismuth. And I'm pretty sure they asked for grams, yeah? Yes. So now we need the molar mass of our bismuth. 208.98. So times 208.98 grams per mole is 105.4 grams of bismuth. All right. And when 228 grams react with 175 grams, how much is formed based on the limiting reactant? All right. So, limiting reactant problem. 6WCl6 plus 8Bi yields W6Cl12 plus 8BiCl3. 228.175. So divide by the molar mass of our tungsten hexachloride was what? 396.54, and the molar mass of our bismuth was 208.98. So 0.575 moles of this guy and 0.837 moles here. It's going to be the tungsten hexachloride, but we divide by each of these. 0.575 divided by 6, 0.0958. Hold on a moment, goodness. Ooh. Oof. Sorry about that. Snuck up on me. And the other one is 0.837 divided by 8, 0.105. So yes, the tungsten hexachloride is our limiting reactant. So 0.575 moles of our tungsten hexachloride times 1 mole of W6Cl12 divided by 6 moles of WCl6 times what is the molar mass of our hexatungsten dodecachloride. I don't remember the molar mass of tungsten. 183.84. So the molar mass of this guy is 1,528.44 grams per mole of our tungsten hex. Okay. So 0.575 divided by 6 times 1,528.44 is 146 grams. All right. So let's double check that. That was 120, I think. Yep, balanced it properly. 105.4. Did I? Yep. And then C, 146. Yes. Awesome. Awesome. 122. Ferrocene, a substance once proposed for use as a gasoline additive, has the percent composition 5.42% hydrogen, 64.56% carbon, and 30.02% iron. All right, what is the empirical formula of ferrocene? Not only will this be the empirical formula, it will be the molecular formula because I recognize this compound. So, grams, divided by 1.0079, divided by 12.011, divided by 55.845. We're converting to moles. .38, 5.38, 0.538. So now we divide them all by the smallest number, and we're going to get C10H10Fe. So ferrocene is pretty neat. I actually made this once in undergrad as just part of a project. So you have these two 5-membered rings on either side of iron. And boop, boop, I believe, something like that. It's an interesting thing. All right. So what comes after 22? 122. 126. Oh, there's the last one. Oh, we're almost done. All right. Assume that gasoline has the formula C8H18 and has a density of 0.703 grams per mil. How many pounds of CO2 are... Hate you so much. All right. How many pounds of CO2 are produced from 1 gallon of gasoline? All right. One liter is 1 gallon. So 1 gallon is 3.785 liters. All right. And and 1 pound, and we have 453.592 grams in 1 pound. Okay, there's my conversion factors. Okay, so how many pounds of CO2? Yeah. All right, we're going to need a balanced equation. C8H18 plus O2 yields CO2 plus H2O. 25, 16, 18. Yes, I kind of have that memorized. All right. So 3.785 liters times grams per mil. What was it? Where was it? 0.703 grams per mil is 703 grams per liter. Okay. So 703 grams per liter times 3.785 liters. $2,660 grams. The molar mass of octane is 114.23 grams per mole. .3 moles of C8H18 times 16 moles of CO2 divided by 2 moles C8H18 times 44.01 grams of CO2 per mole of CO2. So times 8 times 44.01. Oops. And then, so that gets us 8198 grams. And now divided by 453.592 grams per pound. Is 18.0 pounds of CO2. Gotta admit, that's a surprisingly large number. I would not have expected that. 126, 18.1 pounds, rounding errors. All right, so that is the end of Chapter 6. I only slightly apologize for skipping that one stupid problem on 118. I just didn't feel like it. A lot of work for not much reward. All right, but that's that. I will see you around. I may be doing more Chapter 7 tomorrow night. Bye-bye.